औज़ुबिल्लाहि मिनश्शैतानिर्रजीम बिस्मिल्लाहिर्रहमानिर्रहीम। आज हम HVAC का एक नया लेक्चर पढ़ने जा रहे हैं और उसको हम कंटिन्यू कर रहे हैं जो पिछले हमने पढ़ा था। साथ में थोड़ी सी उसकी रिवीजन भी हो जाएगी और हम इंशाल्लाह उसको आगे भी बढ़ाएंगे और देखेंगे कि कब हम सिंगल स्टेज से मल्टी स्टेज पे हम जाएंगे, चाहे वो फिर कंप्रेशन हो या मल्टी स्टेज इवापोरेशन हो या कंडेंसेशन हो, हम जाएंगे। तो सबसे पहले इम्पॉर्टेंट चीज़ ये है कि हम ये समझें कि जो पिछली दफ़ा हमने किया था उसमें और जो आज हम करने जा रहे हैं उसमें फ़र्क क्यों है और हम क्यों मल्टी स्टेज कंप्रेशन साइकिल क्यों इस्तेमाल करते हैं। सो ये आपके सामने वही जो पुराने कर्व्स हैं वो यहाँ पे आपको शो हो रहे हैं। हमारे पास दो TS डायग्राम पे अगर हम देखें और PH डायग्राम, तो हमारे पास ये दो कर्व्स हैं। जो हमारे पास सैचुरेटेड लिक्विड वेपर मिक्सचर है, ये यहाँ पे हमारे पास मिक्सचर होता है। अब हमारे पास कंपोनेंट्स जो होते हैं वो हमारे पास कंप्रेसर, कंडेंसर, इवापोरेटर और एक्सपेंशन वाल्व होता है। अब हमारे पास 1 to 2 जब कंप्रेशन होती है तो हमारे पास बेसिकली आइसेंट्रोपिक कंप्रेशन होती है और यहाँ से बिल्कुल ये प्रेशर हमारे पास राइज होता है ड्यू टू कंप्रेशन फ्रॉम 1 to 2। तो हमारे पास 1 से 2 पे कंप्रेशन होती है और बेसिकली कंप्रेसर वर्क हम इनपुट देते हैं और कंप्रेसर वर्क करता है, जिसकी वजह से हमारे पास जो प्रेशर है वो राइज हो जाता है फ्रॉम 1 to 2 and the process is isentropic, so whatever is S1 would be S2. Now further, the heat rejection in the condenser takes place. So from 2 to 3, the heat rejection from the condenser takes place basically from 2 to 3, the heat is rejected. As you can see that the liquid has been actually, that the superheated vapor has been actually converted into a saturated liquid. From 3 to 4, the expansion valve comes in and the process of throttling come in, and the process does not remain isentropic. In fact, it is the isenthalpic expansion, and the isenthalpic expansion was shown like this from 3 to 4. So it means that the entropy has been increased from 3, because at 3 the entropy was here, you can see S3, but at 4 the entropy has been increased, but the process has been isenthalpic, which I am going to show on this pH curve. And then from 4 to 1, the process of evaporation takes place, and what actually happens that the heat is absorbed, or the heat in or absorbed. So the heat is absorbed by the refrigerant, and a saturated vapor has been obtained at 1 ideally, because we are discussing the ideal vapor compression refrigeration cycle. Now what will happen on the pH curve? So you can see that these green line are actually the constant entropy line. The isentropic processes would be shown on this line, on these lines. So from 1 to 2, as you can see that the process is isentropic, and the green lines are showing over here the isentropic lines. So from 1 to 2, basically the isentropic compression takes place from 1 to 2. So from 1 to 2, the isentropic compression takes place. From 2 to 3, as you can see that there is a temperature drop, so the temperature would be dropped, but as you can see that whatever is the pressure at 2 would be the pressure at 3, so it is an isobaric process, so the pressure over here would remain constant and it would be a horizontal straight line. So this is how it can be shown over here from 2 to 3. So from 2 to 3 we have basically the heat rejection process, isobaric heat rejection, the condensation process takes place. Then from 3 to 4 the isenthalpic expansion takes place, and whatever is the enthalpy at 3 would be the enthalpy at 4. So whatever is H3 would be equal to H4. These are all the old points which we have discussed already. Now from 4 to 1 the heat addition, again at a constant pressure, the heat absorption takes place from 4 to 1. Ideal vapor compression refrigeration cycle. So this is basically from 4 to 1 the evaporator is here, the evaporator is active, evaporator, because the heat is being absorbed by the refrigerant, and over here the condensing or the condensation process takes place because the heat is rejected. So from 2 to 3 the condensation process takes place. As you can see that from vapor it is converted into saturated liquid, from superheated vapor to a saturated liquid, and from here basically a mixture of vapor liquid mixture has been converted into saturated vapor ideally. Now this process or this cycle is actually in one stage. You can see that the evaporator and the condenser process or the compression process is taking place in one step. But sometimes in most of the applications in the chemical industries and the pharmaceutical industries and the food industries, dairy industry particularly, we sometimes needs this evaporator, the refrigerant to evaporate at a very low temperature. For example, at minus 40 degrees Celsius, minus 50, minus 80, even sometimes minus 120, minus 100. So this temperature actually goes way below, and for a constant condensation temperature, first we are going to assume that the condensation temperature is constant. So if we keep this temperature constant over here, so whatever is the temperature over here, if remains the same, so by increasing this gap, as you can see that if we reduce this temperature, so this gap between this temperature and the evaporator temperature would increase. So this is what we call this gap, or we would call the temperature lift. So this lift actually increases the gap, basically this gap basically between the evaporator temperature and the condensation temperature increases. Now due to which some of the problems arises. How? So let's move towards that. Now again, these are the same TS and pH curves, and we are going to see that what are the differences between these curves and how these curves behave basically when we reduce the evaporator temperature, and we continuously go on reducing the evaporator temperature of the cycle. So now if you see in a TS diagram, so if we reduce this temperature, as you can see from this T4, which is actually equal to T1, and T2, which is T3 basically. So if we actually increase, if we keep this T3 over here, so it is the same, whatever it is, the same T3, it is same, and we actually reduce this temperature. So the temperature has been reduced, so a bit, we are going in bit and pieces. So now for example, the temperature at 4 has been actually shifted. Actually it was over here, as you can see from the above figure. So actually it is over here, so I am drawing it. Actual was here when the gap was same, when there was T4. Okay, now if we increase this gap, so it means that we will need another curve, and the process would then come towards here, and let's suppose like this, and then it will move like this and like this. It is actually, I am making it a bit So now you can see what is the problem. The problem is that from 4 dash to 4 double dash, we have reduced this temperature to 4 T4 dash and this temperature to T4 double dash. Now what is the problem? The problem is that you can see that what was the entropy. So the entropy here was S4. See, now here the entropy is S4 dash and here the entropy is S4 double dash. Now you see that the entropy is actually increasing, and now if the entropy increases, which means that the vapor is increasing more. As you can see that this is moving towards this vapor line and the vapor is increasing. So in this mixture the vapor is increasing, the percentage of the vapor liquid mixture is actually increased, and now it is quite difficult for the evaporator to work over here, because it is quite difficult for this evaporator to work under this condition, or it is simply impossible for the evaporator to completely convert this into a saturated vapor. Secondly, even if it converts this into a saturated liquid like this, let's suppose like this, or like, actually it was like this from 4 to 1, or let me draw this curve again from 4 to 2, and this is 3. So this was the actual curve. This was the curve which actually has been shown in this figure. Now when we reduce the temperature or lower the temperature of the evaporator, now what happened, that this will happen. So this is going to happen, that as you can see that this, now this is 1 dash and this is 2 double dash. Now you can see that a quite big amount of compressive work is required. See, first the compression was from 1 to 2, but now when we reduce this temperature, so a lot of work input is required. Now we have to the compressor have to do a lot of work, and we need a more amount of energy and a more operating time for the compressor to compress this saturated vapor into a superheated vapor. And similarly, further reduction, you can see that it will further increase this temperature into 2 double dash, from 2 dash to 2 double dash. So you are going to see that the more we move down, the more the evaporator temperature goes down, the more you need the input work for the compressor, and so the more you need the work input, and which actually affects the efficiency of the cycle, because you are removing a small amount of heat. You are actually removing from here a small amount of heat, because most of this is already in a vapor. So you are removing less amount of heat from here, as you can see, and you are giving input work more than what you are actually removing, or what actually it is absorbing. So the point is that the efficiency has been simply dropped. The cycle has not been efficient more, because the amount of work input should be less. For an ideal cycle or for an efficient cycle, the amount of input work should be less and the amount of heat it removes should be greater. But over here, as you can see, that the amount of work input is more and the amount of heat absorbed is less. Similarly, from this superheated steam, you can see that now we have the temperature has been raised very high. First it was over here, as you can see, over here, but now the temperature has been raised over here. So the temperature has been raised, and now we need a more efficient condenser and more amount of I would say a sophisticated condenser to remove this heat and then to become this liquid, a saturated liquid. So it is quite difficult. So the efficiency has been dropped. So it means that this cycle in a single stage can work if the evaporator temperature is in the minus 30 degrees Celsius or minus 40 degrees Celsius. But even for some time for minus 40 degrees Celsius, the single stage ideal vapor compression refrigeration cycle does not work. So we have to then move towards the other solutions. So this is why I can also show this on this curve, that see, from 1 to 2 it was like this, from 1 to 2 actually it was like this from 1 to 2, which was the input of the condenser, but to the compressor. But if we move downward, so you can see that the work has been increased. The work has been simply increased. A lot of work now you need, 1 double dash, 1 dash, 2 dash, 2 double dash. So a lot of work you have to require if I move it to the same pressure, because the pressure is, we have to reach to the same pressure curve. So over here the space is not enough, so we have to reach it to a specific pressure, and a lot of work is required. So as you can see that the work is increased, as well as the efficiency has been reduced, because it is quite difficult for the evaporator to handle a liquid vapor mixture, because it will remove less amount of heat, because as you can see that over here we need a condensed liquid, a liquid which is condensed so that it can absorb the heat and get evaporated. But if more than 50% of the liquid is in a vapor state, so what does that mean? It means that only 50% of the liquid would actually get the heat and convert into vapor, which is actually a disaster. So that is how you can see that these processes takes place. So now the problem is that how we can actually handle this problem, how we can actually overcome this problem. So for that, first let me tell you, I have actually mentioned that, but let me tell you that what happens when we decrease the evaporator temperature for a given condenser temperature. We are not changing the given condenser temperature. The similar effect would be produced if we keep the evaporator temperature same and increase the condenser temperature. So the same effect would be produced, the same hurdles. If we keep this temperature same and increase this one, again the gap has been increased, and again the amount of work required work would be greater. So it is an either way. Either you keep it the evaporator temperature same and the condenser temperature higher in certain applications, or you actually keep this condenser temperature constant and decrease the evaporator temperature. So either by increasing the condenser temperature or by decreasing the evaporator temperature, in both the cases the gap increases between these two limits, and that is why then the problem arises. Now what are the effects? So let me tell you. The effects are, number one, the throttling losses increases. As I have mentioned that, as you can see that as we move down, the throttling is happening from 3 to 4. So as the temperature is reduced, so now you see that entropy is increasing, which means that the losses are increasing. So the throttling losses are actually increased. Number two, superheat losses increase. How? Now you can see that over here the temperature was here. Now the superheating, it is more become superheated, and when this is superheated, so there are losses. The condensation would not take place efficiently and there would be losses. So from 2 double dash to 2 to 3 there would be immense losses, which were the superheated losses. The compressor discharge temperature increases. Now again this is the same, that as you can see that the compressor, now first the compression was taking place up to this temperature. Now the compressor is as we are moving down, the temperature has been increased to this much. So you can see that the discharge temperature has been immensely increased, and we actually do not want that, because we want a cool liquid, a relatively cool liquid to exit from the compressor, because it would help us in a condensation process. Now the fourth one is quality of vapor at the inlet of the evaporator increases. What I have shown over here, as you can see that more quality of vapor has been introduced, which is not required, which is not the case. We do not require this. So the problem is that the vapor at the inlet of the evaporator has more vapor, has the high quality vapor, which is not required. So this was the point, that the vapor quality has been improved, which is not actually required at an inlet of evaporator. because at one evaporator we need a liquid which is in a in a saturated liquid state, so that it can absorb more and more amount of heat, so that the more cooling effect has been produced actually. So if the half of the condensed liquid is already in a form of a vapor, so it means that the half would be the efficiency of that cycle, even less than half, because the work input has been more. So obviously the efficiency has been compromised. Last, the specific volume at the inlet of the compressor increases. So obviously specific volume at the inlet of the compressor increases, which is not required actually, because you have to then, as you have seen that if the specific volume, because see now it has to do a lot of work, so it means that the specific volume has been increased, and that is why it needs a lot of work to be done. So due to these I would say the drawbacks or the effects of lowering the temperature of the evaporator, or keeping the evaporator temperature same, or moving the condenser temperature away, in both cases the gap would be increased. Even in the third case, if we move both of these, if we move the condenser in upward direction and the evaporator in the lower direction, so the gap will again increase. If the gap increases, so then the single stage compression is actually of no use, or I would say of not actually the best cycle for the process of refrigeration. So then what will happen as a result? Now you can see that what will happen as a result of all these things. What will happen? The refrigeration effect decreases, as I have mentioned, because less amount of heat would be absorbed, and work of compression increases, thus decreasing cycle efficiency. So that's what I am actually continuously saying, that the work input of the work of the compressor would be increased, and the heat rejection would be decreased, and that is not what we required in a refrigeration process. We required that the more heat is absorbed at an expense of less work input. Now, then what is the solution? So here comes the solution. So here is the solution, and the solution is a multi-stage refrigeration system. Now, a multi-stage system is the refrigeration system with two or more low side pressures. By low side pressures we mean the evaporator pressure, because as you can see in this diagram, let me show you that evaporator is at a lower pressure and the condensation is taking place at a higher pressure. So when a particular cycle or a particular system in which there are two or more than two low pressures, so in that particular system or that particular refrigeration system would be called as the multi-stage system. There could be basically different types of the multi-stage system. So on that basis we have actually used the classification of the multi-stage system, and the one is multi-compression system. We have multi-compression system, that in which we do multiple compressions. We are going to see that inshallah in the coming lectures. Then we have multi-evaporator systems. Then we have the cascade systems, and so on and so forth. So we have different types of classification of the multi-stage system, because multi-staging can be in different systems. It can be in a compression process, it can be in an evaporation process, it can be even in the condensation system as well. So where we actually introduce the intercoolers and the intercooling processes. But before moving on, we have to discuss two things, and that is actually the flash gas removal. So before we move on, so we have to discuss the flash gas removal and the intercooling process So we have to discuss the intercooling as well as the flash gas removal before going on into all these processes which actually we have mentioned. So in today's lecture I am going to just focus on the flash gas removal using flash tank, and then the intercooler will be discussed in the next lecture inshallah, and then we will move on that how the multi-stage actually works. So this lecture is going to be in different parts, so we are going to move in bits and parts and cover this lecture because it would be a bit complex for you guys to understand in a one go. So you have to actually go through my lectures particularly again and again so that you can understand that what is going on. Now, what is flash gas removal and how actually the flash tank work, so and why that is important to remove the flash tank. Now what happens that when the liquid comes from the condenser, so it is actually not fully condensed, so it has basically the vapors. Now we have to remove that vapor because it would actually make it difficult for the compressor, as we have already discussed that it would make it difficult for the compressor to compress a liquid vapor mixture. So we need a liquid state for the compressor to compress. So we have to remove that gas or that vapor from the let me show you over here. As you can see that over here it is a mixture. So we have to remove that vapor which actually from the condenser or from the throttling process that takes place. So we have to basically remove that vapor which actually remains during the condensation process. As we all know that 100% condensation in a one stage or a one go, when the temperature gap or the temperature lift is very high, as I have mentioned. So in that case we need a flash tank. Now how the flash tank works and how it actually what happens in the flash tank. So I've just named it 6, 7, 3, 8 and 9. So as you can see that from the 6 the liquid comes from the condenser. So from condenser, so the liquid comes from the condenser and it basically has a mixture. It has a mixture of both liquid as well as a gas. So we have to remove that gas. Now what happens that this is a floating wall. As you can see that it is a floating wall. When this level decreases, so this wall gets open, the mixture come in, and when this tanks become full, so this wall closes, and it is, remember, the expansion takes place. So when the expansion takes place, so the liquid comes in over here and the vapor moves through this valve in the upward direction. So the vapor moves in the upward direction and it actually moves towards the compressor, because the vapor has not been actually compressed 100%. So we need a liquid at the evaporator. Basically, as I have mentioned already, that we do not require a high quality over here. Quality of vapor at the inlet of the evaporator increases, and we do not want the high quality vapor. We need a high quality liquid at the input of the evaporator. So that is why we actually sent this vapors to the compressor in order to compress it again and to make it sure that the vapor is being converted into liquid. And then from here the liquid is actually expanded through an expansion valve. It is an expansion valve, and the liquid actually further expands, and upon expansion the temperature further reduces, and what happens, it moves to the evaporator. Now as you can see that the problem has been solved, that this liquid, which was actually having a mixture of the liquid and the vapor, was coming from the condenser. So the vapor has been separated and moved towards the compressor, and the liquid has been expanded into the evaporator, and now the refrigerant which is moving or inlet at the evaporator is a saturated liquid, is not a vapor, is not a mixture of vapor. So that is how the flash tank works, and the flash gases which actually forms upon the expansion or from the condenser or through this expansion. So we have to introduce a flash tank in between in order to remove the flash gases, which actually upon the flash, some of the particles get into the vapor state. So we have to remove that vapor or the gaseous state or the vapor state refrigerant and then send back to the compressor. Now the pH of this particular happening or this particular scenario which I actually discussed of the flash tank or the flash gas removal. So let me actually tell you that what happening that at P6, now this is P6, which is the pressure from the condenser. So here is P condenser. Now you can see that the condenser, so this is 6, at 6 we have a saturated liquid. So upon expansion from 6 to 7, as I have said that upon expansion the flash takes place, and due to that flash some of the saturated liquid converts into the gas, and you can now see that from 6 to 7 there is a pressure drop due to the expansion. This is 6, this is 7. So from 6 to 7 there is an expansion, and due to this expansion there is a pressure drop, and now you can see that the pressure is at P7. Now this pressure will be the same whatever is the pressure at 8, because after this the pressure is not going to change. So from 7 to 8 there would be a liquid state, saturated liquid. From 8 to 9 there will be actually again an expansion, because there is an expansion valve and there is again an expansion. 9 at a lower pressure further, P9, and now you can see that from 6 to 7 and then from 7 to 8 there is a liquid, saturated liquid, and from 8 to 9 there is again an expansion, and actually the mixture which was over here initially has been reduced, so the vapor content has been reduced. Further the liquid vapor actually generated due to this expansion. Now what happens from 7? So from 7 two things are going to happen. From 7 two things are taking place. One, from 7 actually the saturated vapor has been arised and a saturated liquid has been arised at 8. So at 3 we have a saturated vapor which has been moved to the compressor. So from 7 it moves towards the 3 as well. So now you can see that from 7 basically we move towards 3 and 8, where the saturated vapor at 3, and as you can see from here it will be the compression then that is going to take place. And then from 7 to 8 actually the saturated vapor liquid, and then upon the expansion and then again it will move towards this, and further we are going to discuss that in the detail of the multi-stage compression. So this is how the process takes place, and this is how the flash gases can be removed from the by the tank, basically by the flash tank. Now the second process which we would actually study will be actually the intercoolers or the intercooling process, how that takes place and what are the effect of the intercooling and why we need that. So we need these processes, and for now it might be a bit difficult for you guys to understand because we have not used them in a particular problem or a combination, because we are studying it separately. Inshallah, when we will discuss the flash tank, flash gas removal using the flash tank as we have discussed, and then the intercooling, and then combine them in a single problem, then it would be easy for you guys to understand the whole concept, that how actually that they combine together and improve the process and improve the efficiency of the cycle, refrigeration, vapor compression refrigeration cycle in multi-stage. So I request you to kindly go through all my lecture again and again, give it a proper time. Daily you have to watch my lectures, and then it will be actually easy for you to understand. If you have any kind of query, ask me. If you have any kind of question, ask me on any platform available to you, and I will try to answer your queries to the best I can. Thank you so much.